First of all, I would like to open our shaders. So going back to our laboratory subfolder, here we have lab 6 shaders. So first, Vertex Shader, which is responsible for transforming our geometry in 3D space. So I'll move it to a side-by-side view. And our render function prepares our modeling matrix, which is stored inside the model object for the modeling transformation. The render function gets invoked for every frame, and so we prepare our transformations. And then we call model render to do the actual drawing. So let's take a look at the model render. So in model render, we verify that unique handle for this uniform is not -1. If it's -1, it indicates that the vertex doesn't have this uniform present in the Vertex Shader program. And if it's not -1, then we call GL uniform matrix 4, which is 4x4 matrix, floating point values. And this is the GLM matrix that we prepare in our rendering function in the main file. And this is where the data gets uploaded to this uniform variable, which now becomes available to all vertices and all fragments. This matrix includes transformation for all rotations, scaling, and translations. So we take our positions and multiply by this matrix. So at this stage, all of our vertices are now in the world coordinate system. And notice that the modeling transformation happens per every object. So in our design right now, the model class is instantiated for every object that we maintained. For example, if we have a cube, right, and if we have a cylinder as two separate objects that we'd like to place in our world, then we will have two separate model objects to support both of these shapes in 3D world, and each model will be supplying its own modeling matrix for transformations performed separately for this object and the other one, right? So we can rotate, scale, move around these objects independently because we can have separate matrices to perform the transformations. Even more so, in our current design, the model class has a pointer to the shader object, right? So this shader initially is organized as an object, and because of this, the shaders themselves can be different for the cube and the cylinder, because we can have the cube model pointing to this shader and the cylinder model pointing to another shader. So this design provides us with some flexibility to organize our objects and position them in our scenery. So anyways, positions of our vertices multiplied by the modeling matrix place our objects in the world scenery. So now we're in the world space, and each object that was designed in their own space, the object space, now is placed in the common space, what we call the world space. So this is now our world coordinates. And just a quick note that the flow of data has to be enabled by these calls to GL enable vertex attributes array. So we do this for the position and normal, for example, right here. So we are enabling these two input vectors to start accepting the normal vectors and the positions of our vertices. This is where we're specifying which shader program we want to use. And then eventually we say we're going to use the vertex array attributes, and we're going to say let's draw our triangles and specify how many total vertices we're using while drawing our object. So once we have organized everything here at the model level and we understand how the rendering works, we can basically close this for now and just focus on how we construct and combine all of these transformations. And this is happening in the main module in our main file render function. So for every frame of display, this function gets invoked. We update our rotation angle, and now we're building our transformations using GLM helper functions rotate, scale, and translate. And if you recall from our GLM presentation, the way these transformations can be combined is that we start to think about translation. So we want to take our object and move it 50 units behind the screen in the negative direction of the z-axis. So this is what we do. We call translate, and it gives us back our translation matrix. But this is the identity. So basically this is pure translation without any combination with other transformations. Then we want to think about scale, and we say we already have our translations in space, so now we can combine translations with the scale. And similarly, the result of the scale gets combined with the rotation. So anyway, so this is like a chained series of calls into these helper functions. This is identical to setting up each transformation matrix independently from the identity matrix and then multiplying them together. However, this approach to change the matrices eliminates this extra step of matrix multiplication and makes things go faster, which is of course definitely what we want to speed up the frame per second rate. But this is what's really important to remember. So you start with the identity matrix and then you combine them together like this, right? So you get your first transformation. So here it is, it gets chained with the scale. Then you get the scale and it gets chained with rotations. But the most important thing to remember is that our direction is going this way. Basically, although we constructed in the sequence of translate, scale, and rotate, the matrix multiplication that is taking place here is that the rotation will be happening first, and then it will be a scale, and then it will be a translate. So in our situation, what we have, if this is a cube and this is our object, then clearly the rotation will take place first, because we want to rotate a certain way. And this is where we specify the axis, the y-axis, so this is why we're rotating around the y-axis. Okay, so then we're going to scale. So the scale can change size, it can become smaller or become larger, right? And then we do the translation. So we take this object and we move it somewhere else. So now with all the changes, rotations and everything, so it's now somewhere here, right? So it looks like this now. Okay, and so this is now in the world coordinates, and this transformation actually is happening in the shader. So here we just prepare the matrix, but then this matrix is going to be used to multiply every position right here inside the Vertex Shader code. So these transformations, rotate, scale, and translate using GLM library, are very easy to construct as long as you remember that you have to construct them in reverse order. Okay, so it's a little misleading, is that it makes an impression that if you're starting with identity matrix right here, it seems like the translation will be happening first. But that's not true. It will be happening the last in the order of these transformations. So now we have our objects in the world space like this. So they're all in common system of coordinates in the world space after this first multiplication. Then we would like to transform this into the camera space. So if this is our observer right here, this is an eye, and we're looking down this way. So this is a negative z coordinate in the camera space, right? So this is the system of coordinates of the camera. So the camera transformation is applied by our view matrix. And finally, if we also want to make it look realistic, we apply the perspective transformation. So the result of the perspective transformation is now this will be in normalized device coordinates and ready to be rendered, at least in terms of the actual geometry. So these two matrices, which are loaded into these uniform variables, are coming from the camera object. So the camera, actually, we have the object here, C++ object, that maintains the properties of the camera, like position of the camera, what kind of orientation it has in space, right? How we position this camera in space. And also, it's just convenience to keep the perspective matrix in the same place, just basically store the perspective matrix also inside the camera class. So this is the name of our camera object named camera, and these two uniforms for the view transformation and the perspective matrix have to be loaded per every frame, and this is where it's happening. Okay, so we have inside the camera class, we have a member function named setUniformViewPerspective, which sets up these two things. So let's take a quick look. Right, so we open the camera class, and here it is, setUniformViewPerspective, and this is where the data for two of these uniforms, the view matrix and the perspective matrix, get loaded into the graphics card. And at this stage, as we construct our world, and this is the negative z direction, minus z, right? And we position our object somewhere behind the screen. So I consider this x and y plane initially to recognize it as our screen right here, right? So this is the surface of our screen. So we position our object somewhere behind. So this is our cube or whatever objects we may position there. The constructor of the camera sets the view matrix to be the identity matrix, because right now we have no means to move the camera around. So what we do, we simply set the camera system of coordinates, the camera space, to be the same as the world, which means that our camera is stationary. It's positioned right here in the origin of the system coordinate, and we're looking down this way. Okay, so we just simply keep looking down the negative z, and that's where we see all of this animation. So the object keeps rotating, and we're looking at it from different angles. And we construct our perspective matrix based on the field of view. Remember, we can specify the field of view right here. Our first term of view, like this, it's basically the angle like this. It's like a rectangular cone shape like this. And we also specify the aspect, the near plane, and the far plane. So we specify where the near plane of this first term is located, and where the far plane is also located. So this creates our volume of view, and we supposedly see our object animated inside this volume. And of course, this constructor is invoked only once, because we construct our object just once. And then the setUniformViewPerspective function call has to happen per every frame, because the camera can start moving and start looking at different directions. So obviously, as this happens, as the camera starts to move inside the world, these updates for view and perspective have to be happening per every frame. So this is our quick overview of the rendering process, and this is where we call this to set perspective and view. And as we prepare our modeling matrix, we give it to our model object, and inside the rendering, this uniform is also loaded for the modeling transformations.